At this very moment, high above our planet, there's a thunderstorm firing massive bursts of gamma-ray radiation. We've spent most of our time on this Earth not knowing this was going on until we discovered it by accident in 1994, when a satellite was pointed in the wrong direction. This thunderstorm looks peaceful from orbit, just a giant cloud system spreading across hundreds of kilometers while pulses of lightning bloom and fade silently inside the white mass. For a tiny fraction of a millisecond, though, that same storm does something no human eye is able to catch. It fires bursts of gamma rays, which is the exact type of radiation astronomers usually link to the most violent events in the known universe. Yet it's coming from inside a common weather system. These gamma-ray flashes vanish long before any instrument on the ground can register the hit. And for most of human history, there was no way for us to even know it was there. When NASA launched the Compton Gamma Ray Observatory, tucked inside was a detector called BATSI, or the Burst and Transient Source Experiment. The team gave it one specific job: to watch deep space for gamma-ray bursts, massive high-energy explosions that detonate in the most distant corners of the universe. At the time, every engineer who worked on the design assumed Earth's lower atmosphere remained quiet at such high frequencies, so they saw no reason to ever look down. Of course, now we know that isn't the case. In 1994, BATSI started picking up short, intense spikes of gamma radiation that didn't match any of the cosmic sources the scientists were studying. No distant galaxy or spinning neutron star lined up with the timing of these signals. And while the readings looked strange, the geometry of the hits were even stranger. Turns out the radiation wasn't coming from deep space, just screaming up from below the satellite, right outside of Earth's own atmosphere. A detector built to track one of the most extreme events in the universe had accidentally stumbled onto something just as extreme inside a regular Earth storm. Since BATSI wasn't designed to monitor the ground, the angles were awkward and the sensitivity was way off, which meant it only caught a few dozen events during 9 full years of operation, which still meant the events were strong enough to be picked up. And even with that limited data, the pattern was impossible to ignore. Researchers eventually named the phenomenon terrestrial gamma ray flashes, or TGFs, which are sub-millisecond bursts of radiation that happen at the exact same time as lightning activity inside storm clouds. They were able to discard the possibility that these were just hardware glitches or ghosts in the machine. No. They were real physical events happening in a place they had no business being, as far as we knew. And a tool built to study black holes had just handed atmospheric scientists one of the deepest puzzles in modern geophysics. The flashes were definitely real, but the actual cause turned out to be even stranger than the discovery itself. Once the initial discovery was made, scientists started using better instruments to point at the problem area from every possible angle to see what they were missing. NASA launched the RESI satellite in 2002, and it measured photon energies up to 15 MeV, which was way higher than any of the early data had suggested was possible. Then an Italian mission called Agile pushed things even further by detecting photons that approached 100 MeV. These flashes were actually producing radiation at energy levels that rivaled what astronomers see from black holes and colliding neutron stars. But the signals weren't coming from the edge of the universe, they were coming from inside the house. To understand how that can even happen, we have to look at physics from the ground up. Inside a mature thundercloud, ice crystals and water droplets are constantly slamming into each other within massive updrafts. Positive charge starts to pile up near the top while negative charge builds up lower down, and the electrical field between those 2 points gets stronger by the second. Hundreds of millions of volts can separate the top of a storm from the ground below, but that field doesn't spread out evenly. Instead, it concentrates most sharply at the very tip of something called a lightning leader. A lightning leader is basically the invisible precursor to the bright bolt we see during a thunderstorm. And it acts like a narrow channel of ionized plasma, carving a path through the air for the bolt to come a moment later. At the very tip of that channel, the electric field can exceed hundreds of thousands of volts per meter across a tiny space. In that incredible concentrated field, a single free electron can start doing something very strange. Normally, a free electron moving through air loses energy quickly by colliding with molecules. But in the extreme electric field at a leader tip, it gains energy faster than it loses it. It accelerates to a significant fraction of the speed of light, entering a state physicists call runaway. That one high-speed electron eventually slams into an air molecule and knocks even more electrons loose. It's like a snowball effect. Those new electrons hit that same powerful field and accelerate in the exact same way, and then each of those goes on to liberate even more. The whole thing scales up exponentially from just one seed electron that happened to be in the right place at the right time. One of the main explanations for these flashes is known as a relativistic runaway electron avalanche, or RREA, and it suggests this self-amplifying chain reaction is the engine behind the flash, even though the exact trigger and the shape of the source are still not known for certain. Here's where the magic happens. As these electrons tear through the atmosphere at nearly the speed of light, every single one of them passes close to the atomic nuclei in the air. That close call causes the electron to deflect sharply, and that sudden deceleration makes it radiate energy outward in the form of a photon. Because the particles are moving so fast, the photons carry massive amounts of energy and come out as gamma rays. Physicists call this breaking radiation, or Bremsstrahlung in German, and it's the exact mechanism that converts the stored electric potential of a storm into a gamma ray pulse. A gamma ray flash isn't really an explosion, but rather the electromagnetic signature of an avalanche of electrons hitting a wall of air. For a split second, the storm does the same thing a particle accelerator does, by taking stored electric potential and turning it into fast particles, high-energy collision, and radiation. The difference is that the hardware for this experiment is just the weather. But the gamma rays are only the beginning of the story. Inside that particle avalanche, some of the gamma photons carry enough energy to interact with atomic nuclei directly. When that happens, the photon actually converts into two separate particles, an electron and a positron. The positron is the antimatter version of the electron, meaning it has the same mass but the opposite charge. In a storm that is strong enough, these pairs are created in huge numbers and launched upward along with the rest of the cascade. When a positron eventually meets a normal electron, both of the particles are instantly destroyed. Their combined mass turns back into energy and radiates outward as two gamma-ray photons that each carry exactly 511 keV. That specific number is fixed by the laws of physics, and it serves as the unmistakable signature of matter and antimatter wiping each other out. In 2011, the gamma-ray burst monitor on NASA's Fermi satellite recorded a sharp spike at exactly 511 keV, right in the middle of a terrestrial gamma-ray flash. This wasn't some broad signal or background noise, but a very narrow and defined peak at the precise energy level that electron-positron annihilation always produces. Fermi detected a signature that proved positrons were being made in a high-energy process in our atmosphere, and then being destroyed as they traveled along the magnetic field of Earth toward the spacecraft, which was 550 kilometers above the storm. We often think of science fiction when thinking of antimatter, but these were real antimatter counterparts of electrons manufactured inside a thundercloud and destroyed in a way that left a clear mark in the satellite data. perfect for us to finally take notice. The strangest discovery of all came from a sensor sitting on the International Space Station. The Atmosphere Space Interactions Monitor, or ASIM, is designed to record lightning, gamma rays, and energetic particles all at the same time. When the data from that sensor finally came back, the entire sequence of events was the opposite of what everyone had assumed. Lightning was the result, the end of the entire process, not the start. First, the gamma ray burst arrived, and the visible bolt that humans have watched and feared for thousands of years only showed up afterward. The bright flash we see is just the final signature of a process that is already finished. A particle avalanche that tears through the cloud in total silence, producing no light, but leaving the visible lightning stroke behind as its exhaust. The case isn't considered closed yet, though. Right now, it's more like a long chain of events running from a storm cloud all the way to a spike in satellite data. But there are still several links that need to be worked out. The biggest open question is why this only happens sometimes. Not every lightning flash produces a gamma ray burst, and the ratio is actually about one event for every 1,000 lightning discharges. We haven't been able to fully explain what separates the storms that produce these flashes from the ones that don't. It's apparent that the shape of the electric field and the way the leader behaves both play a role. But two storms can look exactly the same on radar while producing completely different results. The specific conditions that push a storm over that edge still remain a mystery. Part of the problem is how hard it is to detect these things. The flashes beam upward in a cone shape, so a satellite only catches one if that cone happens to sweep across its position in orbit. Most of these events miss every single detector we have, and current estimates put the global rate somewhere between hundreds and thousands of events every single day. So the fact that the range is so wide shows how much the beam geometry messes with our count. Fermi logged about 4,000 events during its first 8 years, but that number only shows what the instruments were able to capture rather than what the atmosphere was actually doing. It's clear to us that storms have been doing this for far longer than anyone can guess, and they will continue to do it, whether we're able to catch them at it or not. As we build better and better instruments and gain more knowledge about these mysterious events, we might be able to unravel the process at some point. But for now, we have to be okay just marveling at the magnificence of the world and space around us.